So we're still discussing some basic foundational information that you need to be aware of in order to design better interfaces. What we will start looking at today is information from the area of psychology. We will start today with cognitive psychology, which is the study of the human brain, not from an anatomical point of view, which is what we did last time, but from a conceptual point of view. How do humans think? One of the most popular models that was proposed to enable us better think of an interaction with a user interface is the model human processor, or the HMA model, by Stewart, Card, Moran, and Newell. The information here is based on experimental findings from a number of studies that has showed how many seconds or milliseconds does a human take to perceive something, to think of something, and to react using his motor skills. In other words, we could imagine that during the interaction with a computer or a software or a piece of hardware or any digital system, three systems are involved, one after the other, inside the human brain: the perceptual system, the cognitive system, and finally the motor system. In other words, the user starts by perceiving the change in the interface, next thinking about what has just happened and making a decision about what to do next, and third, moving his arms or eyes to respond back or to initiate another action. I will try, while explaining this model, to connect to the anatomy of the brain so you understand how the two fit together. But I have here a word of warning for you, is that cognitive psychologists, when they work at a much higher level than the anatomy of the brain. As I mentioned at the end of last time lecture, there is a huge disconnect between what actually the brain does and what we record using a device like EEG. The reason why is our devices do not have enough resolution, spatially and temporally, to record all the details. Cognitive psychology as an area exists before the invention of brain recording devices. Scientists who work there rely mostly on doing experiments directly on the user or the human without the assistance of a brain recording device. It's only recently that we started to see research works for cognitive psychologists using brain recordings. Now, a lot of time what they propose, although it looks like it's common sense correct, there might not be a lot of factual information or proof from the anatomy of the brain that this is happening. But as researchers start doing brain scanning, they realized actually there is actually an evidence of what was previously believed to be correct in certain situations, and there are counter evidence for what was previously thought to be correct. However, the HMA model, the good thing about it is that it's based on experimental evidence for most part, even though it's a little bit high level and a lot of details are skipped, but the general idea of thinking of the interaction using the HMA model has been proven to be quite useful. So let's start, and the details will become clearer as we discuss the topic. So here is another view of the HMA model. Whenever a change happens in the interface, you are perceiving it using your senses. The senses could be your vision system, or using audio, if you're interacting, for example, with a phone-based interface or a sound-based interface. For example, also, if it's not a phone-based interface, a sound-based interface like Alexa, Amazon's Alexa. Followed by a cognition part, and finally, you deciding to make an action. So I'm going to work on the model step at a time. So I will work first, or I'll describe and explain the sensory part first, and then we'll move to cognition and motor later on. Now, the word perception is used to describe all the inputs that you can get from the environment. And it's not just seeing. Usually perception is misunderstood as seeing, which is an inaccurate or an incomplete understanding of the word. Everything you perceive includes what you see, what you hear, what you smell, what you touch, even what you taste with your tongue. So all of this is perception. All of these are inputs into your brain, and not just seeing things. And as we will see, there are differences between those input modalities. Now, if you have been following carefully what I'm saying, I started by saying that we will study the different branches, or we will learn information from the different branches of psychology, including cognitive psychology and perceptual psychology. And the reason why they are different is because perception is before cognition. So perception psychology is related to the processing that happens in the occipital lobe of the input data coming from the optic nerve, for example, if we are talking about what are you seeing, and sending that to the frontal lobe. Cognition happens in the frontal lobe. Perception happens in the occipital lobe and other areas. So we differentiate between them because, remember, when we talked about the brain, we said that the brain consists of processors, almost like the CPU in a computer, except it's a much more sophisticated device. Currently, the most sophisticated CPU you could get is what, like a quad core or maybe an octa core? While in the brain, apparently there are incredible number of these CPUs. So whatever is happening in the occipital lobe when the information is received from the eye through the optic nerve is not yet in the frontal lobe. It is actually in the occipital lobe being assembled. So you could think of the occipital lobe as being an assembler or a collector of lines and dots and colors, putting them together, and then later on sending them to the frontal lobe. And there are generally two pathways to send information to the frontal lobe. As I have highlighted here in the chart on the right, if you're looking at an object, the information about the object, including its color, texture, shape, and size, is then sent through the left hemisphere. The information about the location of the object, if the object is moving or not, if the object is performing or performing any special transformation, like continuously rotating around its y-axis, or its x-axis, or its y and x-axis, or where is the object in relation to other items. The object is under the tree, the object is on the desk, and so on. This spatial information or spatial processing is sent through the right hemisphere. Now, the picture on the left is telling us the whole story of seeing things. You got the eye, we talked about it in detail in lecture 1. You got the optic nerve coming out from the back of the eye, going directly into the brain, and finally it's arrived at the occipital lobe in the vision center. And then the image on the right takes effect, where the information is sent using two pathways through the right and left hemispheres. Now, it is believed that the perception is done in the occipital lobe. The cognition is done in the frontal lobe. Now, obviously, there has to be some kind of communication between the different parts of the brain. But the perception starts at the occipital lobe. So, if we try to map what we know from the anatomy of the brain to the HMA model, the perceptual processor is really somewhere in the occipital lobe. Okay? While the cognitive processor that we're going to talk about in the second phase of the HMA model, or as the second component in the HMA model, is going to be in the frontal lobe. Now, what's the proof to that? Nowadays, with brain scanning studies, we can actually prove that. We can use or set up an experiment in which we prove that the perceptual processor brain wave or brain bands, delta, alpha, theta, beta, and gamma, gets activated first before the frontal lobe starts to get activated. So that perception happens in the perceptual processor. But this is, again, remember, doing brain scans is a relatively new phenomenon. Historically, perceptual psychologists always argued that perception happens first and then cognition later on, by examples like the one in front of you. If you actually try to understand what you're looking at, you will not. But you are perceiving it correct. If you look at the far right where the stairs, if you look at the part that is closer to you, or the edge that is closer to you, the stairs are climbing up, and then suddenly you find yourself, you're down instead of up. The same thing if you look at the figure at the center. If you try to find where is the inside from the outside, where is the front from the back, and you're completely confused. What is confusing here, or what's confusing you, is that your cognitive processor is not making sense of this. It contradicts what you have stored in your memory of objects and pictures and rectangles and so on. The same thing for the box at the left. It just does not make sense. But you are perceiving it correct. So this was an example of a proof that perception is something and cognition is something else. The fact that you see something, you collect the dots or the lines, you connect them together, you present them to the to the frontal processor, does not mean that you understand it. It just means you have perceived it. So we are going to study a number of theories in the perceptual processor. They all coming from perceptual psychology, of course, and they help us a lot in the design of interfaces. Okay, so let's start. The first thing we need to understand is that the perceptual processor, just like many processors in the brain, in fact all we know, is discrete, which means it's as if it has its own clock. The cycle time, which is basically the time to do anything, you can draw an analogy here with the instruction set inside the CPU. If you remember from your hardware courses, there is the fetch, decode, execute cycle. You cannot get anything faster than 3 ticks to do fetch, decode, and execute. The same idea, the same concept exists in the perceptual processor. The cycle time is 100 milliseconds, which means you cannot perceive something independently in less than 100 milliseconds. Okay? This is the shortest time you could do anything. You cannot do anything shorter than that. Or let me be more specific, you cannot perceive anything in shorter time than that. Now, based on this 100 milliseconds, there is a number of actually important findings or perceptual theories. The first one is the theory of perceptual fusion. The two stimulus within the same cycle appear fused. They appear as one. Okay? This is the reason why when you studied graphics, you were told that in order to have the animation smooth, you should have it at least 10 frames per second. Sorry, at least greater than 10 frames per second. Because, as you know, in a second, there's 100 milliseconds and 10 frames per second or more. If you actually make it 10 frames per second, you will see 1 frame per 100 milliseconds. And you can distinguish between whatever happens Well, let me just again be more clear. You can perceive accurately whatever happens in 100 milliseconds. But if you cross the 10 frames per second to 11 or 12 or 15 frames per second, the two frames adjacent to each other, let's say the first and second, or second and third, or third and fourth, because they are displayed less than 100 milliseconds, they will appear fused. And this is what you see as smooth animation. The opposite of that is flickering. Flickering is coming from a slow frame rate which keeps a frame displayed for 100 milliseconds or more. So you see one frame, then you see the next, then you see the next, and between one frame and another, you see the first frame disappearing and the second one appearing, and that's flickering. But if you exceed the 10 frames per second, you will see them fused into each other. Okay? Because you cannot detect anything less than 100 milliseconds. So the first and second are fused into each other. The second and third are fused into each other. The third and fourth are fused into each other. And consequently, you see smooth animation. Okay? Now, also a result of this theory is that if you present a result to the user in less than 100 milliseconds, so the user clicks OK, and the response comes back in less than 100 milliseconds, the user will think that no time has elapsed, because the user can only detect things happening after 100 milliseconds. But within 100 milliseconds, they look like it's 1 unit of time to the user. Okay? So if you're looking for instantaneous feedback, then you have to target less than 100 milliseconds. Now, within the 100 milliseconds, it doesn't matter if it's 50 or 70 or 90, because for the user, it's 1 unit of time. It's 1 perceptual cycle. Okay? The user will feel that they are the same. Which, if you think actually deep about it, it actually gives you some leeway in terms of what you can do with the processor. If you go back to your operating systems course, that means you can interleave tasks, and as long as the response is always coming back within 100 milliseconds, then the user will not notice that anything has happened. And this is actually what happens inside operating systems when you do context switch between running threads. You don't get a sense. You might be working on Word, and actually the CPU was taken away from you. You're writing a document, the CPU was taken away from you, and you don't feel it because the application actually itself somehow was frozen, but you don't realize that, okay? Because it's less than 100 milliseconds. So the takeaway is that perceptual fusion occurs when two stimulus within a cycle of 100 milliseconds appear fused, okay? Now, the second complementary theory related to the 100 milliseconds issue is that the theory of perceptual causality or causality, depending on your British or American English. Now, what is this notion of causality? Let's imagine the following. You're playing a pool game, like the one in front of you, and with the stick you hit the white ball. The white ball moves, it hits the red ball. But after it hits the red ball is not moving. 100 milliseconds elapse, and then the red ball starts to move. Would you think this is normal? The answer is no, because if the white ball hits the red ball should move right away. The word right away here really is used to refer to the 100 milliseconds. So let me read the first bulletin. It says, two distinct stimuli are perceived as related if the two events occur in the same cycle. The first event appears to cause the other. This is common sense rule from real life, okay? Imagine you go to a room and you switch on the light by flipping the switch. And then you walk into the room and the room is still dark. And after a second, the light goes on. It will feel very strange because when you switch on the light, it's supposed to switch on. The bulb is supposed to light on right away. Okay? It doesn't light on after 2 seconds. It doesn't make sense. Okay? The same idea here. In order to engage the user inside any game, if you think of game design, or applying this to game design, you want to make sure that the user actions are followed by reactions from the software within 100 milliseconds, because that causes what we call perceptual causality. The user immediately recognizes, oh, I did this and this is the result. Okay? Now what if it's not? What if it's more than 100 milliseconds? What actually happens, the game look awkward and it's almost like flickering in animations. There is something going on that is not right. You hit a guy with a bullet in a shooting game and the guy doesn't die right away. He keeps standing, the game freezes, or you keep moving and the guy is not dying and suddenly he falls on the ground. Well, maybe this is not a good example because that's how people die in games, but the general idea is you need to relate the action with the reaction to the action. Okay? And that relation has to be done within 100 milliseconds. Okay? Now, good games actually, good game engines, what they do is they calibrate the hardware. The software is being installed on to make sure that the two theories we're talking about, perceptual causality and perceptual fusion, are always respected, because that affects the gaming experience. So they would run benchmarks, or they already come loaded with benchmarks, and they detect your processor, they detect your hard disk configuration, they detect the amount of virtual memory you have, and they will decrease their frame rate and change in the game details, maybe in the screen resolution, to make sure that everything happens within the 100 milliseconds as planned. So the takeaway is that perceptual causality is detected by the user when two distinct stimuli are perceived as related if the two events occur in the same cycle of 100 milliseconds. Now, the second takeaway is that in a highly interactive interface, it is important to support perceptual fusion and perceptual causality to avoid affecting the user experience. The second thing we're going to look at is how we actually perceive things. Okay? Now, there's a story behind that, because for a long period of time, perceptual psychologists used to fight with each other. And by the way, in psychology, it's common to use the word fight because researchers used to really fight against each other. And if you haven't been exposed to psychology literature, you will not have an appreciation of what I'm saying. These guys would write papers responding to each other as if it's a public fight. So, for example, one researcher might publish a theory about XYZ. Another one does not like what or does not believe in the theory. So he goes to write a paper that will get published with the title "In response to the flawed XYZ." And then someone else would write a paper saying, "I believe XYZ is correct," okay, or "in support of XYZ." So these guys used to fight a lot with each other. And you have to give them some leeway, because they do experiments on humans, and there's lots of ethical rules around doing experiments on humans. So the restrictions set sometimes force them to do experiments in certain ways, and consequently the results they come up with might be doubtful. Anyway, so let's try to understand how do we perceive things. The first theory we're going to look at is called the top-down theory, or the constructive theory. Now, in the top-down theory, it goes like this. Those who support this theory historically used to believe that whatever you perceive is based on your previous experience or your previous perception. The information that you have stored in your brain that is related to what you are currently perceiving will be used to perceive what you're looking at. Okay? A very famous experiment that tried to prove this is the one that I am putting an image for here. The researchers got a number of users or participants and divided them into two groups. In the first group, they showed them figure 3A. And then later on, they showed them figures 3C and asked them, okay, what is this? So the answer was, it's a sketch of a man's head. Then second group was shown figure 3B. which is an image of a mouse. And then later on they showed them figure 3C and they said it's a sketch of a mouse. And that was a proof that we use previous knowledge to perceive what we are looking at or what we are trying to process. Okay? In other words, what our brain is doing some kind of pattern matching, trying to follow through the lines and match it with the closest line drawing or texture that we know of. Now, this is one way of thinking about how we look at things and how we perceive them. There is another, and now before I move on, this is a nice example. I forgot about this one. If I tell you what are you looking at, you will tell me I am seeing an image of Mel Gibson. But if you actually look closely, you will see that his nose is nothing but a guy sitting. His mouth is nothing but a stone. His hair and face is made up of 2 trees. So this is again an example of top-down processing. You see, if you looked at the trees and you didn't look at anything else, you would have said trees. You would have said a boy, trees, a box and a stone and some grass. And 2 huts, which are his eyes. But you saw Mel Gibson, which means you abstracted the drawing to the highest level thing you know of that is close to this. And that is top-down processing. Okay? You didn't go after the details. You went after the big picture. So you relied on stored information and you match it with Mel Gibson. So you said, oh, it's Mel Gibson. Okay? This is a proof again of top-down processing. Now there is another theory, which is bottom-up processing. In bottom-up processing, you trace the lines and dots with your eyes from the smallest detail to the bigger detail to the biggest detail to make a decision. For example, if I tell you, what are you looking at here? You will tell me, at least one option is, I am seeing a man playing a trumpet. Or I am seeing a girl, a side view of a girl's face, which is the white area on the right side. Now, you could not have done that unless you've traced the lines. Okay? You must have traced the lines to construct something as close as you can, and that can only be done by tracing the lines. So this is an example of bottom-up processing. So you look at size, you look at shape, you look at orientation, you trace the lines, colors, textures, and so on, little bits and pieces from here and there, and then you suddenly realize, okay, this is what I'm looking at. Now, nowadays, the fight has been resolved. We know that in our brain we're doing both. This is a study I'm citing for you. You can read it, but it's not really mandatory for the course. But if you would like to convince yourself, we are actually doing both. In our brain, we do both, and the one that resolves or enable us to perceive faster will be utilized. So the 2 processes are working in our brain, bottom up, top down, and the one that wins every time is the one that guides us to perceiving what are we looking at. Okay? And by the way, this proof is obviously, as you noticed, is coming from an EEG study, and these are heat maps which I described in last lecture. So let's put a takeaway. The perceptual processor supports both bottom-up and top-down processing of input. Standard interface relies on top-down processing to save learning time. What's the story here? Okay, why am I saying an interface should rely on top-down processing to save learning time? Here is the story. The worst thing you can do in an interface is to be, I'm here stressing the word standard. I'm talking about an interface for Windows or Mac or Android. Okay, the worst thing is to force the user to try to think, what is he looking at? To spend time doing perception. And you will make him spend time doing perception if you provide an interface to him that is completely new, that violates all standards. Because what he's going to do is he's going to trace the lines and the dots and the textures and the curves, trying to figure out what is this. Just like you spend more time with trying to figure out, is this a man playing a trumpet or a girl face? So top-down processing relies on previous stored information. So when the user opens a new application that he just installed, it should look like any other application on his device, whether it's a laptop or a tablet or a PC or a cell phone or a smartwatch even. It should look like any other application for that device. That's why companies who manufacture hardware would make a standard, and you need to follow the standard. So innovation in user interfaces does not mean that you bring a completely new interface. That's a research activity. It's not for general population kind of consumer applications. Okay, typical consumer would like to see or work with an application that he has seen something similar to before. Now, that doesn't mean that you copy interfaces of other applications. It means that you respect the standard. So he tries to map top-down what is he looking at compared to what he knows. Okay, if someone has already been working with Android for 10 years, any new application he installs, he expects to be an Android-like application. Okay, the drawer, for example, can be pulled from the left or from the top, as an example. You should not have it pulled from the right bottom corner of the screen. Okay, so top-down processing is generally preferred for standard interfaces. Now, when we talk about the research, that's something else. You have the complete freedom to do whatever you'd like. But when we talk about standard interfaces, don't be a standard breaker for the sake of innovation. Okay, you have to stick to the standards because that enables top-down processing. The next thing we're going to talk about is the Gestalt theory. Okay, now Gestalt, as I've written here, it means the essence or shape of something. And Gestalt theories focuses on what's called perceptual organization. How does the perceptual system try to organize the scene it is looking at, if you're talking about vision, so that it can understand it faster or better? Okay, now these obviously are coming from perceptual psychology. They were developed by German perceptual psychologists. That's why the name Gestalt is German, and they have very important implications for us in user interface design. So let's start to see the Gestalts. Now, here are the Gestalts. I've listed them for you. They are called similarity, symmetry, proximity, awareness, common fate, continuity, closure, figure, and ground. Okay? Now, let me try to highlight the importance of these Gestalts. When you're looking at an interface, we said that the optic nerve is going to take the information to the occipital lobe, which is the center or the place of the perceptual processor. The perceptual processor is trying to make sense of what it receives. At that level, we're talking about lines and dots. Okay? These low-level, or these gestalts, are low-level filters. You can think of them like that. They are low-level filters. They always are there. You could think that each one of them is almost like a program that gets invoked. Either the program returns positive results, or it returns a message that says, I cannot work. If you manage to design an interface that invoke these gestalts, you are speeding up the processor or the work of the perceptual processor. Now, if you don't, you're going to still perceive what you're looking at. The perceptual processor will still be able to handle the situation by trying top down and then bottom up, or maybe, as I mentioned, both, trying to make sense of what is perceiving. But if you go through them, through the gestalts, it's much faster. Okay? So you are actually helping the user. And in fact, these are so low level and so embedded in our perceptual processor or in our perception that this is actually what differentiates between an interface or even a picture or even an illustration or even a postcard, a one that you look at and you feel something about that attracts you, versus a feature or something about it that just makes you feel that it's not good to look at. Okay? The notion of aesthetics itself has a lot to do with these gestalts, as you will see. Okay? When you say that this is a beautiful interface, or a beautiful painting, or a beautiful postcard, or a beautiful magazine cover, or a beautiful ad, it has to do a lot with these gestalts. Okay? It's almost there's a reward system that you feel by invoking these gestalts, and they can only be invoked if you actually design for them. So yeah, obviously you have to learn them to design for them. So let's look at them one by one. The first one is called the proximity gestalt, or often referred to as the law of proximity. What this tells you is that stimuli that are close together will be seen as a group. So if you look at these two images, and I tell you what are you seeing in each one, in the left you will tell me I am seeing 4 circles. In the right you're going to tell me I am seeing 2 groups, each of 6 circles. So the grouping was done because the circles in each group are closer together in terms of white space compared to the other group. So the distance between the 2 groups is bigger than the distance between the circles in a group. And this is what proximity is about. If you would like to tell the user these things are related, then you would have to invoke the proximity by making them closer together. This is an example of what I was just describing. If you look at these 2 forms and I ask you which one is better to look at, now you will keep looking and then you will tell me the one at the bottom. The reason why each row is actually one unit. It's the username, label, and the text field you're supposed to enter the username in. It's the first name, label, and the text field you're supposed to enter your first name in. When in the first figure we put them way apart from each other, you're not seeing it this way. You're seeing it as 2 groups, the labels as one group and the text fields as another group. But it's not supposed to be like this, because the group is really the username, label, and the text field label. And that is what actually you're capable of looking at the bottom figure. And this is what I'm referring to. You are going to see the wrong grouping, and this is kind of irritating to your perception and cognition as well. It's not supposed to be like this. Either you see as one big group, which is at the bottom, which will kind of make sense to you perceptually and cognitively, or you see it as 2 independent groups, as you see in the above figure. Now, this is another application from a user interface in forms, in building forms, utilizing the law of proximity. When you look at this form, you feel that it's well made. The reason why it's well made, the designer used indentation to group the fields in one section, under one title, together. So what you're looking at is 3 groups of fields, not just a bunch of fields, but 3 groups of fields. Okay, that's what you're actually seeing, and that's why you feel that it's well received on the eye, okay, or in your perception. Now there is something else here. If you look closely, the utilization of the distance between the labels and the next line is not the same. what you're seeing, my name, first name, and then the last name, they look, because the distance looks smaller, even by few pixels, they look as one unit. And then the next unit comes in the next line, the next unit comes in the next line, and so on. So you could apply proximity recursively into your form or in your design, not just at some high level, but even at the nested levels within that high level. And that's what you're seeing here in this form. You can see this even here in this snapshot of a website that has some articles. When you look, it will not take you a lot of time to figure out that you are looking at 3 articles, and you can read each one of those articles by clicking on the read more at the bottom. Again, it's the space between the articles that make you conclude that there are 3 separate articles. So when you're reading, you're not gonna continue reading from the lines of one article to the lines of the second article. So not say behind a product or adapt their design. You say behind a product or interface can be, and you continue on. Okay? And this brings us to the issue that, design, if you go to a design school and attend any design course, they will tell you design is not about filling the space. It's about the empty space. How you manipulate the empty space gives you a better design. Okay? And proximity is the classical or the first example that would come to mind. Okay? Proximity is all about manipulation of white space. And that's what you're seeing here. Now, here is also another example from a user interface. And if I tell you which of the two is easier to perceive, and you will tell me, if you keep looking, it's the one on the left. Because by grouping the buttons together, your eye does not jump between them. They are one logical unit. These are the actions you can take in this dialogue. So it makes sense to bring them together. Okay? So the takeaway is that you place user interface elements that are related close to each other, and as a group, they should be distant from any other element. And this will activate the proximity gestalt. Again, remember, proximity gestalts and all the gestalts are like programs that the perceptual processor pipe through them the perceived, or if we're talking about vision, the viewed scene, and either the gestalt gets activated or it doesn't get activated. Your goal is to activate them, because this is actually what is a good interface supposed to do, because it speeds up the perception. Now let's look at another gestalt, which is the law of similarity, or the similarity gestalt. This says that items that share some property or attribute are perceived as belonging together. Okay? If I tell you what are you seeing in the right image, you will tell me I am seeing red triangles, green circles, and gray squares. If I tell you what are you seeing at the left figure, you tell me I am seeing circles and squares. Okay? So the more properties common items or similar items share, the more it is easier to perceive, because you will group them as one. Okay? And this is what similarity is all about. You play with colors, you play with shapes, whether in the foreground or the background, to invoke the gestalt, so the user feels that, or the perception decides that these are one and the same. This is the same dialogue we looked at before. We said that the one at the top doesn't feel right on the eye. If you would like to keep it with this layout, your solution would be to put a common background to the label and the text field. So now when you're looking at it, it's easier on the eye. Why it's easier on the eye? The common background color will invoke the similarity gestalt. And consequently, you're thinking now that the username and the text field at the same row have the same background, so it's one thing. So instead of thinking them as two different things, which is what you see in the top, you're seeing them as one. And this is what I'm referring to. That's the changing or making the background color the same, or the shape the same, or the object the same, or the highlighting the same, introduces this or activates this similarity gestalt. So the takeaway is that associate related interface elements with each other using visual cues such as common background color, common shape, or common highlight. And this will activate the similarity gestalt. The next gestalt we're going to look at is what's called the continuity gestalt. Now, in this gestalt, what happens is that the dots that could be grouped together that form a single continuous path or flow or layout or border will be seen as one. Okay? And it is interesting that experiments has shown that the continuity gestalt overrules proximity. In other words, if your eye can travel after, or your perceptual processor can travel after a series of dots to make a path or some kind of pattern, it will do that. Okay? It will not try to associate by proximity, but it will just continue on following the dots to make some kind of a pattern. For example, if you look here, and I tell you, like, what are you seeing? You will tell me, I'm seeing a curve that goes upward or a curve that goes downward. Okay? Your eyes are tempted, or your perceptual processor is tempted to follow on the dots. Okay? You don't stop and try to tell me, like before we have seen with proximity, oh, I am seeing 2 groups or 3 groups of circles. There is one going from left towards the center, another one from the center going down towards the right bottom of the screen, and then another one going up. You know, it's not like that. You are following the curve. Okay? Now, continuity is extremely important in interface design. As I mentioned, it overrules proximity. Now, why is it so important? I want you to look at these 2 images we have at the bottom and tell me which one is better to look at, or more accurately, to perceive. It's not about the content, obviously, because there is no letters here. It's just a sketch of something. Now, you should have said that it's the one on the right. The reason why it's the one on the right, your eyes are tracking quickly through the content of the page, and it doesn't like to stop. What's irritating to you on the left figure is that your eyes stop because of the interleaving of text and images. While on the right, when you trace through the text, you don't stop because of the image. This is continuity. And in fact, it is done at that level because whenever you see something, you don't read it right away. Remember, we talked about how you see things in the first lecture, and we said that you always see a blurred image in the first instance of looking at something, and then your eye gets adjusted, so you're seeing crisp vision by adjusting where the fovea is. So whenever you look at any piece of text, before you actually start to comprehend the letters and the words and the phrases, your eye is scanning what it's looking at, trying to organize the content in front of it. And that's perception, by the way, that's not cognition. So you're going through, somehow, somewhere in your brain, in the perception of an image of a document that looks like the one I've put at the bottom right or the bottom left. The question is which one is to perceive faster. And again, continuity means follow the dots or follow the lines. The more you follow the lines, the more you're going to invoke the continuity gestalt. And on the one right, obviously, you're going to follow the lines enough, you invoke it. On the one on the right, on the left, even from now when you're looking, it just doesn't look right. Okay, this doesn't look right because you're not invoking the continuity gestalt. Now, continuity gestalt appears in many places. This is one example. This is the Microsoft ribbon. If you are not familiar with the history of Microsoft Office products, this was not the common interface they had. For many years they had the traditional file menu, and then you open a dialog, and then you see these options in a dialog. Now, what they did a few years back is they switched to this ribbon that shows up here. Basically, they got the content that existed inside the dialogues and they exposed it to the outside, in the toolbar of the application. Okay. Now, the question is, where is continuity here? Well, actually, it appears in a number of places. What they actually smartly did, the designer who designed this, is that every section that exists here, if you look, for example, at the paragraph part, there is a section that's related to the indentation. All the indentation icons are very similar to each other. Okay? So when you're looking at them, your eye doesn't stop. All the figures that exist in the drawing pull down are all similar in style to each other. Okay? So the trick with continuity is that you let the eye continue on and do not stop it. For example, if they introduced a white row in the drawing pull down, you see where it says A, and then there is a tilted line, and then there is an arrow, then there is a rectangle, then there is a circle, then there is a rounded rectangle. Let's say at the next line there was a white space. You would break the eye flow because there is nothing in the space, so the eye would just disconnect the first row from the second row, which is going to be the one that has the star. So by having them visually similar, this ensures that the eye does not stop. And continuity is about the eye not stopping, continuing on with the content. So the takeaway: organize user interface elements one after the other in a continuous fashion. This activates the continuity gestalt. As long as you maintain the same style, the same theme, then there is a chance of invoking continuity. The next gestalt we're going to look at is the Prägnanz gestalt. It says that reality is always organized or reduced to the simplest form possible first. Let me show you an example of this. We said before 2 times that when you look at something, it's going to be blurred first. Okay? But that does not prevent you from recognizing what it is. Okay? Why? Even though when you look at the document the first time, the one that appears on the far left, you're not going to see anything because your fovea has not focused yet. You know it's a document. And when you start to focus, you know this is a line, or this is a text, or this is a paragraph. Okay? So you go from the higher level to the more detailed. This is very important for us because we're never capable of getting sharp vision all the time. As I've explained in detail in lecture 1, we go from blurred to focused to blurred to focused to blurred to focused. We don't feel it at all, but it's always happening. So this Prägnanz is helping us in identifying when we look at something and it's still blurred, what it is. Okay? We would reduce it to its simplest form. I don't need to actually even decide to think, about whether this is a document or a movie. It's a document. Okay? Even though I didn't see the lines. And this is Prägnanz. Okay? When you see something movie, you know it's a movie, even though you don't know what's the movie. Okay? Why? Because again, this is Prägnanz. Okay? Now, where do we see this in user interfaces? Okay? On Windows and on Mac, you have an ability to display icons in a big size. When you're actually browsing through a directory that has many files and you're looking for a specific file, this feature will enable you to identify the file, especially if you don't remember its name. You will identify the file even though you cannot see any of the details inside. Okay? You know you're looking for, a textbook. It's just enough to see the first page without knowing even the title, without knowing, or reading the title or the author or the file size or the file name, that this is the one you're looking for. Okay? For example, if I'm looking here for a map, it's very clear to me where the map is. Okay, I don't need to even open it to know it's a map. But I'm not seeing a map. In fact, at this level of resolution, I'm not seeing anything at all in the map. Okay, but I know it's the map that I'm looking for, or at least it's a map. Okay, now why? Because of pregnances. Okay, whatever that we receive, we try to reduce to the highest form using our perceptual processor. You could think of it as almost like putting a label, like I would like to label this, and pregnances help us to label it quickly. Okay, this is a map. Okay, even though we have no clue what's inside this map now, but I know it's a map. Okay, so this is a feature that exists in operating system that relies entirely on pregnances, that actually this is going to help us. We know it's going to help us because we know it exists and it works. Okay, so the takeaway is to provide the user with an overview of information or data. You do not need to use higher resolution rendering. Okay, this appears even in e-commerce websites when they display very small images of products. Even though the user might not see any detail in the product, but once the user sees the image, it will know that this is the product they're looking for or not. Okay, so for example, if you're trying to buy, for example, from Amazon, Levi jeans. So, and let's say you always wear Levi 514. You would even know what's 514 without actually looking at the garment details or the title of the jeans, because you know what Levi 514 looks like. Okay, it's going to be below the waist and maybe relaxed fit and regular legs, not slim legs. Okay, so you don't need more than just a single snapshot of the thing and a very small one that doesn't show any detail, and then you reach to a conclusion. Oh, okay, it's what I'm looking for. Okay, and this appears in almost e-commerce websites nowadays, and even in file managers, as I showed you in operating systems. Now, the next gestalt we are going to talk about is the symmetry gestalt. That you have this filter in your perceptual processor called the symmetry filter that detects symmetry. It gets excited whenever it sees symmetry, and this is actually one of the gestalts that is related directly to aesthetics. That you achieve a lot in terms of the beauty of what you are designing if you respect symmetry or if you implement symmetry. Okay, so this is actually what you're seeing bottom here in these images. Okay, if I tell you what are you seeing, you will tell me I am seeing one bracket and the opposite of it. The symmetry attracted your eye or your perceptual processor. Okay, where do you see this? I couldn't find a better example for from the Taj Mahal. If you look at this postcard, which was very famous back when there was postcards, printed postcards, there's no more symmetry here than I could describe. Okay, if you draw a line in the middle of this mosque, you will notice that everything on the right, there is a copy of it on the left. You have one small minaret on the right, and there is a corresponding one on the left. You have a big minaret on the right and a big minaret on the left. You have two domes at the far right of the image, and then you have one dome that is quite the size of the two of them on the left. You have trees on the right and left of the canal. You have the pavement, the red pavement, replicated on both sides of the canal. If you look at Taj Mahal itself, the windows are mirror image of each other. If you draw a line in the middle, you can see symmetry on both sides. Okay, the reason why this image, even though it's very low quality, I found it as a GIF online, and it's probably a scan of a card that was printed back in the 1970s, as you see from people's clothes. It's perfect symmetry, and this is why people like Taj Mahal. Apart from the story behind it, the engineering here is perfect in terms of the utilization of symmetry. Okay, now even the trees, the trees on the far right, you have trees on the far left. Okay, so where do you see symmetries in user interface? We're seeing it nowadays in many places. Most websites are trying to respect or implement the symmetry or invoke the symmetry gestalt. So here's an image or a screen capture from CNN. What you're seeing are 3 columns that are symmetrical, and the images are also symmetrical, and the titles under the images with the titles, subtitles below them. There is, a lot of symmetry in what we're looking at. This is why this looks good on the eye. Okay? Now, the idea of symmetry can be easily implemented by employing a grid system. So you draw a grid, you divide the screen into 4 quadrants, and then you continuously divide each quadrant into further 4 quadrants and further 4 quadrants nested, and so on. And then you fill in the content. So you get this effect of being perfectly symmetrical. Okay, so the takeaway: organize your interface taking symmetry into consideration horizontally and vertically, and this will activate the symmetry gestalt. And as I mentioned, this is one of the main measures of aesthetics, of being beautiful, okay, that you have symmetry in place. Another gestalt is the law of common fate. That when you notice that a number of objects have similar marker or identification or direction or color, you are also implying to the user through the common fate gestalt that whatever happens to any one of them will happen to the rest of the members of the group. Okay? You can see this being utilized in user interfaces as in the next slide. If you look here and I tell you which one is better to look at, and if you keep looking between the 2 images, you will tell me the one on the left is somewhat better. Why? Because by coloring or highlighting the icons you're going to delete, for example, you have invoked the common fate gestalt visually. Now on the right side, you are going to delete those 3 records, number 4, number 5, and number 7, but it requires a step of thinking from the user, and that's going to happen because you are actually highlighting or putting a mark in a place that is not what is going to be deleted. What you're going to delete is Nilo Mumbai, okay, or Nilish Poon, okay, or Bharti Chennai, okay, but you're putting the mark somewhere else. You're not highlighting what's going to be deleted. You are actually not doing that in the right, but you're doing that on the left image. Okay, now the left image is actually invoking the common fate gestalt for sure. The next one needs some kind of proxy, and ultimately you reach to a conclusion mentally or cognitively that, yeah, I'm going to actually delete those guys. Okay, but here, before thinking about it, you know that they will have the same fate. On the right side, you have to think that they will have the same fate. Okay, so the left one is actually invoking the common fate gestalt. So the takeaway is that to communicate to the user that a functionality will be applied to a number of objects, attach a distinguishing feature to all of them. The next gestalt we're going to look at is called the figure ground gestalt. You see, when we perceive things, we don't have control on the light rays that goes into our eye. So we are seeing a lot of things in any instance. What these gestalts enable us to do is to organize the scene into things we should focus on, or to converge into the things with our perception on the things we need to concentrate on, and put the other things in the background. Okay? Now, that's if the scene is organized that way. In other words, if you would like to invoke gestalt, you have to reorganize the scene so that this gestalt is actually invoked. So whenever you would like to tunnel the user attention to a specific item on the screen, you have to organize it as figure versus ground, or background versus foreground. This is an example of that. When the user is requested to enter his email, okay, there are 2 ways you can do it. You can take him to a page, and prevent him from moving away from that page until he enters his email. But if this is so important and you would like to attract his attention, what you do is you dim the background and you display what's called a pop-up modal dialog on top, so that his focus is on this dialog that is now as if it's actually, illusion-wise, it's in the front. Obviously, this is a 2D screen, so there is no physical front versus physical back. There is no depth, real depth. But presenting it this way invoke the gestalt. So the user is now focused on the foreground and the background is hidden away. Okay? And again, if you do that, you make the perception easier, because his perception will be tunneled to your dialog where you say, please enter your email. So the takeaway: to direct user attention to a specific user interface element, disable and dim background and show the element on top. The next gestalt we're going to look at is the closure gestalt. This gestalt is actually very interesting because it enables us to complete the picture even though there are missing parts. For example, if I look at the image on the left, I will see a black triangle with some missing portions, and I will also see 3 circles with some missing segments. If I look at the figure on the right, I will see 4 circles with some missing segments as well, but I will see the circles. Okay? Now, this is something that happens all the time in our brain, in our perceptual processor. Whenever there is something missing, it will complete the picture for us. Okay? For example, if you look at this logo, you're not going to tell me I'm seeing a bunch of dashes. You are seeing IBM. Okay? You will complete the letters and you will read it as IBM. Similarly, if you look at this dog, every time I actually show up this, I forget whether it's a dog or a hound. Anyway, every time the students will tell me, but unfortunately this time I won't hear it, the student will tell me what's the name of this. So you are seeing it, even though there's lots of details missing. Okay? Why are you seeing it? Your brain actually is completing the picture. Now, this gestalt actually exists even in audio. In fact, it's heavily used in the advertising industry. You see, in the advertising industry, whenever you listen to or watch an ad on TV, the sounds that they say or the statements they say, there is always a chance that they are playing with this gestalt. So instead of completing the whole sentence, the actors in the ad, they would say part of it and they will leave the rest for you to complete in your brain. And by this they actually save some seconds, and you know that in advertising they charge by the second, so that it might actually make them save significant amounts of money. Okay, so this exists visually, and it exists also auditory in your brain. It also exists on many e-commerce applications or websites, where you start seeing parts of an item but not the whole thing, and you can still complete the picture, the mental picture in your brain. Okay, your ability to figure out that actually this is the side of the pant and that this completes this one, or if I see this then I know what's the rest, is again invoking indirectly this gestalt. So, take away: when short on-screen real estate, you can show partial content and the user will complete the picture, and this is the closure gestalt. Now, I have here an example for you that uses all the gestalts, with the exception of one. I want you to just watch the video or go to the website where I got this from and see the difference between the starting design and the final design. You for sure will agree with me that the final design is much better aesthetically, it's much better on the eye, you can perceive it much better if you'd like, or easier or more relaxed, and the reason why is it's invoking a lot of the gestalts. Okay, so you can just hold on until the last one And here you go. This is the original, and this is the final, and obviously the final is much better. Now, Gestalts have been a topic of research in the HI community because we know that aesthetics and organization of a user interface is influenced heavily by the utilization of Gestalts. So I am actually citing for you here one research work that will take an interface and reorganize the interface elements to invoke as many Gestalts as possible based on the number of elements and the type of elements you've actually passed. Okay? And I predict that in the future, user interface builders will be using such tools to produce designs that are easier on the eye, that are perceptually they are better, and they also have some aesthetics in their design. So watch the video and follow the details there. Now we'll move on to the remainder of the processing theories we're covering today. Let's talk about the stores. Okay, we have actually stores in the perceptual processor. Okay, remember, if you think vision-wise, again, you get a feed of information from the optic nerve. Okay, the information is stored as an image that you're seeing from your eye in the what's called visual information store. Now, it decays very quickly. So anything you see within 70 to 1000 milliseconds, within a second, it will go away. So if you see something suddenly as a snapshot, okay, it's difficult for you to remember it later on because it stays only for a short period of time before it disappears. Interestingly, the auditory information store, the information stays there longer. So whatever you hear, you can still recall. This is actually has implication on user interface design. Whenever you call a support system on the phone, and they will keep giving you options. If you would like to talk to the support, press number 1. If you would like to talk to technical support, press number 2. If you would like to report stolen whatever, press number 3. Otherwise, stay on the line. Okay. They could give you even 5 or 6 options. And after the message finishes, you can still remember the options. Why? Because you were just hearing them, they went into your auditory information store and they're still there. Okay? But we cannot do the same for the visual information store. You cannot display instructions to the user and tell him, if you would like to do this, then this is how you do it. And if you'd like to do that, then this is how you do it. And then the user closes that window and you expect him to remember anything from what he just saw. Okay, because the information stays for a very short duration in their information store, in their visual information store. Okay, I can tell you also about a funny phenomenon related to the auditory information store. If you've ever been in your car and you get this guy driving a car, usually he's a guy, rarely I've seen as a girl, usually a guy who will be sitting in a car beside you, and he has the volume increased to the maximum, which wonders. I always wonder, like, what's wrong with his ears. So after he leaves, let's say he turns right and I turn left, and he's far away from me, and I can still hear the same noise. Okay, why? Because the sound went into my auditory information store, and it will stay there for a while. So even though the guy left and I cannot even see him in the mirror, I can still hear boom, 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 boom in my ears. Okay, it's coming from my auditory information store. Okay, because the decay is much slower than the visual information store. Now, the next thing we're going to cover from the perceptual psychology is what's called the lateralization of images and text. Okay, now there is an interesting anatomical fact, which is that what we see with our right eye is processed in our left brain or left hemisphere, and what we see with our left eye is processed in the right hemisphere. Now, so what? Well, there is actually an implication of that, because uh, images and text are stored in different locations in our brain. Okay, so we would like to position the images and text in relation to where they are stored in our brain, because that speeds up the perception. So the takeaway here is that I will position images and graphics on the left, and I will position text on the right. Why? Let me read what is written here, which I got from a research paper. A stimulus presented in the left visual field is initially received and processed by the right hemisphere, and a stimulus presented in the right visual field is initially projected and processed by the left hemisphere. Let me read the other one. Because the right hemisphere is better suited to process pictorial information and the left is more logical and verbal, placing the image on the left-hand side of the text enhances the processing of the whole message. Okay? So when you position the images and graphics on the left, they will be transferred to the right hemisphere, because they are transferred always to the opposite one according to the anatomy of the human brain. Now this is good because on the right side, the pictorial information is processed and believed to be encoded and decoded. Okay? While on the left side, logical and verbal information is encoded and decoded. So if you position images on the left, you are speeding up their perception. Well, if you position it on the right, it's still going to be perceived, but it's a little bit delayed. And the complement is also true. You should position titles towards the right, okay? Because that means it's going to be transferred to the left hemisphere, which is more suited to the encoding and decoding of textual and verbal information. Okay, you can see this applied many places, especially in advertising, labels, in big ad panels on the streets. The position of the images and text, because you usually glance at it while you're driving or while you're passing by. So the position makes a big difference compared to, for example, reading a web page online or even a book. It doesn't matter that much because the delay is not going to be that significant. But to enhance the chance of the user perceiving what they're looking at, say on a highway or while passing by, usually these rules you will find them strictly followed.